Hello and welcome. In this video lesson, we are going to take a look at the method of proof by induction. So there are often a lot of claims that cannot quite be proven with techniques such as direct proof or even proof by contrapositive, and we'll look at such a case. But let's go ahead and start off with an interesting example. And throughout this, I would like you to pause and see if you can think about these individual problems on your own before you hear me solve them. So first of all, let's consider a 2x2 checkerboard. That means it has 2 rows of squares and 2 columns of squares. Suppose you place a single square tile on one square from the board. Assume that an L-shaped piece consists of 3 individual squares as shown. The question is it possible to cover the remaining board with non-overlapping L-shaped pieces? So what we're saying for a 2x2 is for a 2x2, we want to ask, can you take a 2x2 square and cover up any one of them and then use the L-shaped pieces to cover up the remaining ones? So we can imagine we can rotate this, we can flip it, we just cannot change the orientation of these 3 squares. So first of all, if I cover one of these up, shouldn't matter which one. Suppose I cover that one up. Well, then I could take this L-shaped piece and I could rotate it so that it looks like this. So I suppose that would be a rotation of about 180 degrees. And then I could, or I'm sorry, not like this, not quite like this. Let's move this guy down here. So rotate it a little bit more so that your L-shaped piece looks like that. And I'm just going to go ahead and draw the L-shaped piece like this because that covers 3 squares in the shape of an L. So far we know that we can do it for that 2x2, but that was assuming that the square that was covered up was in that corner. Well, on another 2x2, and once again, I would like to ask you to pause throughout this to see if you can make sense of it before we go and look at it together. So suppose that that square that was covered up was here instead. Well, once again, now in that case, I could just use the original L-shaped piece and I can cover up the remaining squares. Now they can't overlap, so that means I can't have part of my L-shaped piece in the green area, which is considered to be the square that is covered up. And I can't have a part of the L piece hang off the board either. Well, that's not the only case, because somebody may say those 2 cases are great, but what about the third case where I cover up the square down here? And of course, once again, we could say, well, if you rotate this thing 90 degrees, then you can cover up those 3 remaining squares with that L-shaped piece. And finally, the last case of the 2x2 would be where we covered up the bottom left square, which is this guy, and then to use L-shaped pieces to cover up the remaining one. That's great, that's for a 2x2. But what about a 4x4? Well, for a 4x4, we'd probably have to do some convincing of ourselves in order to establish whether or not that's true. So let's move on to a 4x4. So for a 4x4, I'm now going to have 4 rows and 4 columns, and once again I'm going to try to do the same thing. But you can see that this is going to get quite more, or considerably more costly to deal with this size checkerboard, because now we have 16 squares. So I really encourage you to pause the video and think about this and see if somehow we could relate this back to the 2x2 case to see whether it's possible for a 4x4. So first of all, we have to cover up any square inside of this. I should be able to cover up any square. So for instance, I should be able to cover up this square right there and tile the rest using these L-shaped pieces. So I can kind of start and I can kind of do that, and I can do that over here, maybe this over here. But I see I've gotten myself into a little bit of trouble because, of course, now I still need to cover up this square and 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 this square, but I can't do it with L-shaped pieces anymore because I can't move the individual squares. It has to be in that L-shaped piece. So unfortunately, I'm not going to be able to do these do these 4 squares or these 2 squares. But if I begin thinking about this in a more careful way, I can actually see that a 4x4 is really 4 2x2s. And if I really think about this one down here, this bottom left corner, as one of the 2x2 cases from above, oh, hey, look, that matches the second case. And so what I can do with that 1 square is put an L-shaped piece there. And therefore, I have completed at least one of the 3 2x2s within that greater 4x4. But then I have 3 remaining 2x2 cases, and none of those look quite like the ones up here. But it would be really great if I could turn all 3 of those 2x2s into situations where exactly 1 square is covered up. So let me do this. Let me put an L-shaped piece across the 3 2x2s like this. And now imagine that really this L-shaped piece, just all it really did is covered up 3 squares. And so as a result, I now have 3 new 2x2s, each of which obviously have to match one of these 4 2x2 cases here, because these all started with 1 square covered up. So now here I can put an L-shaped piece there, an L-shaped piece there, and an L-shaped piece there. And let's just consider one more 4x4 case, because maybe what I did was really made this somehow a special case. So here we go, roughly our new grid. And so once again, I'm going to continue thinking about this as a set of 4 2x2s. And now if I cover up any other square, I don't know, let's pick this one up here, then how do I tile the rest with L-shaped pieces? Well, of course, this top right 2x2 looks like one of my cases from up here. It looks like this one. So, it looks like, yes, this one here. So I can just put an L-shaped tile there. But now again, I have 3 more 2x2 cases that do not have 1 square covered up. However, if again I link these 3 with one L-shaped piece like that, now I've essentially created a similar set of 3 additional cases where there's exactly 1 square covered up in each 2x2. And now you can see that I can cover up those two, and those 2. Let's just consider one more case. So if we, again, look at something like a 2 to the third by 2 to the third, we ultimately want to ask, can you prove this is the case for any board with dimensions 2 to the n by 2 to the n and 1 square covered? It is safe to assume that n is an integer, that n is in the set of integers, and we want to be able to justify our reasoning. So here is a 2 to the third by 2 to the third checkerboard, and you can see that this gets conceivably more difficult because it's larger. But let's go ahead and again think about dividing this 8 by 8 into 4 4x4s. So it'll look kind of like this if I create a division there and a division down the center. You can see that really what I have is 4 of the previous case, the 2 to the 2 by 2 to the 2. A 2 to the 2 by 2 to the 2, i.e. a 4x4, consisted of 4 2x2s. So an 8 by 8 consists of 4 4x4s. And once again, I have to be able to arbitrarily place cover up any one of the squares. So let's say this one right there. I covered up that square. How would I tile the rest? Well, this 4x4 is already taken care of by virtue of the fact that we know that we could break this up into 4 2x2s. So let me do that with a green pen here. So if I broke this up into 4 2x2s, we see that that is exactly one of the cases that we know how to handle in the 4x4 case. So now I can take my L-shaped piece and perhaps cover up these 3 squares here, again creating 3 more 2x2s that all match the structure of this initial 2x2. And so now I can put my L-shaped piece there, put one here, put one here, and put one here. And the problem is that took care of one 4x4 case, but I have 3 more 4x4 cases that do not have a single square covered up. But guess what I'm going to do? I am going to link the 3 squares via an L-shaped piece. Each 4x4 is going to have 1 square covered up by this L-shaped piece. And now I have created exactly this case up here where the green shading is just represented by the components of this L-shaped piece here. So now I can once again create my 4 2x2s. This 2x2 here, I'll cover up those squares, and then again I'll take an L-shaped piece and connect the remaining 2x2 squares and be able to take care of those guys. And I'll do the same thing here. Here's a 2x2, take care of that. I have 3 more 2x2s. I'll connect those with an L-shaped piece, fill in the rest. And once again here, this 2x2 I'll fill in like that. I have 3 more 2x2s that need to be taken care of, and I'll connect those like so. And you can see that it is always going to be possible because I can always create the next case from the previous case. So what about, what can you say if the board, well, we're not going to worry about that question right now, but the question is, can I do this, continue doing this for larger n? This kind of proof is a little bit different than other proofs that we've considered because we're trying to ask, can we do this for a 2 to the n by 2 to the n for all n? For all n. Okay, so when you're trying to prove something like this, it's difficult to do because there are infinitely many integers. And as a result of there being infinitely many integers, you would have to consider infinitely many checkerboards in order to prove this. Unless you could somehow reason through, well, here's evidence that it works for the smallest case, a 2x2 case, and then use a couple of examples just to yourself to be able to reason that you could extend that principle, looking for a pattern of how the previous case connects to the next case. So let's say something like this. Suppose a 2 to the k by 2 to the k checkerboard can be tiled this way. For some arbitrary integer k. In other words, what we mean is that we have some 2 to the k by 2 to the k board. Now, I don't know what k is. K could be 10 or 15 or 30. The point is that this is some arbitrary, meaning we're not specifically saying this is 2 to the 5th by 2 to the 5th. Because if we did that, then our reasoning would only apply for a 2 to the 5th by 2 to the 5th. So in other words, suppose that you can tile this, this 2 to the k by 2 to the k, that you can completely checker this, this size board. Okay? Now, the pattern that we're noticing is this. Consider, and notice that we're saying assume, suppose a 2 to the k by 2 to the k checkerboard can be tiled for some arbitrary integer. So assume that this one can already be tiled. Consider k plus 1. So now we are looking at a 2 to the k plus 1 by 2 to the k plus 1 checkerboard. Now, we've already kind of reasoned that if you increase the exponent by 1, you just create 4 of the previous case. And you can see that here by properties of exponents that 2 to the k plus 1 is 2 to the 1 times 2 to the k. And normally when we multiply bases, we add their exponents. And this right here is 2 times 2 to the k. And if I rearrange this as just four numbers being multiplied together, you can see that if I bring the two individual 2's out front and just leave this as a 2 to the k times a 2 to the k, then I basically have 4 2 to the k's by 2 to the k. And so because I'll have 4 2 to the k by 2 to the k, so we will have 4 2 to the k by 2 to the k's. And so now when I consider this 2 to the k plus 1 by 2 to the k plus 1, I'm going to see it as this whole thing here is 2 to the k, and this whole thing here is 2 to the k. But if I split this thing down the middle and split it across the middle like this, then each of these right here is going to be a 2 to the k plus 1 by a 2 to the k plus 1, because we're going to have 4 of those. And now suppose that any square is covered up. So suppose there's some square covered up over here. Well, I already know that this I'm sorry, I made a mistake in my, this should be, these are 2 to the k's, and the whole picture is 2 to the k plus 1. And this is 2 to the k by 2 to the k. Well, I already know that we've said that suppose we found some 2 to the k by 2 to the k that can be tiled if you cover up just one of the squares with that green shading. So we already know this one here can be tiled by our, suppose that a 2 to the k by 2 to the k can be tiled. But now I have, once again, 3 more cases that are 2 to the k by 2 to the k, but do not start off with having one square covered up. However, if what I do is I once again use my observation that now if I connect the top 3, or these 3 little squares that'll be here, here, and here with an L-shaped piece, I've now created 3 more 2 to the k's by 2 to the k's that look like the 2 to the k by 2 to the k that has one square covered up, and we already know from our suppose that it's true that 2 to the k's can be tiled completely with just one square covered up. So what have we done here? We have shown that basically that if it's possible for some arbitrary case for that checkerboard to be tiled, then it is also possible for the next size up to be tiled. So if any 2 to the k by 2 to the k checkerboard can be tiled with one square covered up and then the remaining L-shaped tiles, we have proven that a 2 to the k plus 1 by 2 to the k plus 1, that is the next size up, can also be tiled. And that means that if you think about the logic, as long as we've proven it for the 2 by 2 case, and we've just established the fact that if it works for one size, it works for the next size up. So we've inductively said that if it works for a 2 by 2, which we've shown that it has, then it must also work for a 4 by 4, because of the fact that we've shown that if it works for the smaller dimension, by this generalization, it works for the larger dimension. Therefore, that automatically states that this works for a 4 by 4. And guess what? If it works for a 4 by 4, if that's our 2 to the k by 2 to the k, then it works for an 8 by 8. And if it works for that 2 to the k by 2 to the k, then it also works for a 2 to the 4th by 2 to the 4th, or a 16 by 16. And we're sort of knocking down all the dominoes by making this general argument about, having made this general argument about being able to tile the higher sizes. So hopefully that gives you a little bit to think about. We are using some general reasoning here, which makes it challenging, but let's think about the logic of what we've done. and why we even need to think about this logic. So many times in coding theory, we write a function involving loops that we claim works for all possible n. For instance, consider the following pseudocode. Nothing interesting happens here really, except we assign 0 to a variable called total, and then we have an index that goes from 1 all the way up to some value n. And every time this thing iterates, all that's going to happen is the total is going to get multiplied by the current value of I. So this is so uninteresting, in fact, that the first iteration total will be 0 times the first I, which is 1, which is 0. And then the second iteration total will take the current value of total, which is 0, and multiply it by the next index, and still producing 0. So basically this is a pretty useless function. But suppose that I wanted to say that this function will work for any value of n, that it basically will multiply all of the totals together. Well, it's easy to claim that, right? That, well, it's a loop, it should always work, but we need to provide some justification, especially as computer scientists. One of the important jobs is to be able to argue and effectively convince people that this code will work no matter what values we feed it. So we make the claim that this block of code will multiply all the integers beginning at 1 and ending at the integer value n. We can certainly test this on a variety of n values, and it may seem obvious to us that it works, but how can we be sure that it works for all n? That's the argument here, that we're trying to prove things that work for all n. This is a justification for which none of our proof methods will work, since there are infinitely many values of n that the user of this block of code may potentially choose. Before we get into it, let's develop something we want to prove. So let's take a brief detour here and think about this problem. Suppose we believe there is an easier and more efficient way to sum a set of integers beginning at 1 and ending at n. We first formulate our hypothesis by looking for better ways to perform this sum instead of doing the following. So for instance, if we were adding numbers of the form 2i plus 1, starting at I equals 0 and ending at n. So imagine this to be a for loop. We're basically just going to add iterations of 2 to the I plus 1 together. Okay, well, so the way this starts off is for a summation, I becomes 0, and now that term is going to be 2 times 0 plus 1. And now I'm going to add to that the next I value, I equals 1, and this is going to be 2 times 1 plus 1. And to that, I'm going to add the I equals 2 case, which is going to be plus 2 times 2 plus 1. And if we look at this observation, we continue to do this all the way up to I equals n. We're going to add to that 2 times n plus 1. And that would be our final term. Now our index is called I. N is a fixed value. I is something that's going to change in value. So that's why we set I equal to 0 and have it go up to some index n. And so really what we're doing here is 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3 and 5 and so on. And these are all just odd integers that we're adding together. So this method works. You can actually manually add these, but it can be computationally expensive for large values of n. Is there a connection between knowing n and coming up with a simple formula to compute such a sum? Let's look at a table to investigate the relationship between n and the resulting sum. Complete the table below. So when I is 0, we're just getting the very first term here, which is 1, and we're not adding that to anything because n is 1. So n starts off at, I should have said let's start n at 0. So if I goes from 0 to 0, it's only going to list the first term. If I goes from 0 to 1, we're going to add 1 plus 3, which is 4. If n equals 2, we're going to add 1 plus 3 plus 5, which is 9. And then here we're going to add 1 plus 3 plus 5 plus 7, which is 16. So 1 plus 3 plus 5 plus 7. And then here we'll add 1 plus 3 plus 5, plus 5 plus 7 plus 9, which will give us 25. And if we add now 11 to this, we'll get 36. So if I want to ask what's the relationship between the value of n and the value over here, the first thing that I notice is 1, 4, 9, 16, 25, 36. I can see the spacing between them is getting bigger, so this can't be a linear function of n. But it does appear that if I look at this value of n over here, that these numbers are perfect squares. In fact, 1 is 1 squared, 4 is 2 squared. So let's make that observation here. This is equal to 1 squared, this is equal to 2 squared, this is 3 squared, this is 4 squared, this is 5 squared, and this is 6 squared. And in terms of how that relates to n, observe that this value right here is actually 1 unit bigger than that right there. And 2 is 1 unit bigger than 1, and 3 is 1 unit bigger than 2, and so on. We can see that there's a connection between the perfect square and the value of n. So I'm going to make the following claim. I'm going to make the claim that the sum of all odd numbers up to n, that a simpler way to calculate this will be n plus 1 squared. And so I can kind of check this. I can see that, for example, if I take here 0 plus 1 squared is just 1 squared, which is 1. 1 plus 1 is 2, squared is 4. 2 plus 1 is 3, squared is 9. 3 plus 1 is 4, squared is 16. 4 plus 1 is 5, squared is 25. And here I'll get 6 squared, which is 36. So I think so far this formula works. So we hypothesize that. We've said that this seems to be more rapidly done by just taking the value of n, adding 1 to it, and squaring it. You don't have to go through the manual process of adding up those individual numbers. We found a shortcut. But here's the question. Does this, we can test this, works for some fairly large n, but we cannot possibly test all possible values of n. We utilize the method of proof by mathematical induction. This method works in the same way that we did the checkerboard tiling. First of all, you got to start somewhere and show that it works for some initial case. In our case, we showed that the base case was the 2 by 2, the 2 to the first by 2 to the first. So we showed that for n equals 1, for 2 to the k equals 1. In our case, that was our index. And so we did go through a few more examples. We did the 2 by 2 or the 4 by 4 and the 8 by 8. But that was just to observe the pattern, to convince ourselves that there is a pattern and to see what it is and then how to work with steps 2 and 3. So the next thing we did, because we have infinitely many cases to prove, we said, assume it's true for some arbitrary case n equals k. Now, that was where we said that it works for a 2 to the k by 2 to the k. And in the next step, and we probably should be careful here, k is a constant, so no, this is okay. This is okay. So we assumed that it worked for some arbitrary constant n equals k. And that essentially we could tile that checkerboard. Then what we did is we showed that it works for n equals k plus 1 by using the assumption from step 2. So now we constructed our 2 to the k plus 1 by 2 to the k plus 1, where one of these cases could already be done, and we made that argument that all you had to do to create 3 more of that same 2 to the k by 2 to the case where 1 square is shaded in here is to use an L-shaped piece to connect the remaining 2 to the k's by 2 to the k's, and those can be done. So the reason this process works is we can think about this as setting up a set of dominoes in a row. If we know we can knock the first domino down, that is, prove the base case, then we know that the base case works. However, we don't yet know that this domino will knock over the next one. So consider each domino to be a sort of representation of each of the different values of n that we can have. However, we now assume, so now here we have like this very first domino. So our base case, what we're referring to as our base case, is just our smallest value of n, which for us was n equals 1, because we could have a 2 to the first by 2 to the first. But we showed it for n equals 2, but the problem with that was, and for n equals 3 even, but the problem with that was is somebody might say, okay, great, it works for the first 3 cases, but convince me that it works for the remaining infinitely many cases. So our line of reasoning was, we just use the n equals 2 and n equals 3 case to develop some logic. And then in here, suppose we have some sort of gap until we hit the kth domino. So there's a bunch of dominoes in between this third one here and this one that says k. We assumed that domino k can be knocked down. That essentially our statement is true for n equals k. This is a trivial step and proves nothing, right? Because you can say, well, assume it works for all of them. And in theory, that if you assume that, then by assumption, you've proven your claim, but it's not good to assume what you're trying to prove. Then what we did is we proved that from the n equals k case, that we could tile the remaining 3 n equals k cases by connecting with that L-shaped piece. So if we prove that k plus 1 follows from n equals k, now we've basically proven that this one can be tipped over. And because this was some arbitrary case, we can also think about now this is the new k, and because that one can be knocked over, this next k plus 1 can also be knocked over. And if we think about that as the new k, and we know that for any arbitrary k that it works, that it also works for the k plus 1 case, well, that knocks over this domino, and you can see that this becomes the domino effect. So that proves from those 3 statements that this works for all n, because if it works for the first case, and by assuming that it works for some arbitrary case, that it always works for the next case, that means that n equals 1 knocks down n equals 2. N equals 2 knocks down n equals 3. N equals 3 knocks down n equals 4. But we had to make this general argument, otherwise we would be limited only to our particular values. So let's see how this will work for our claim here for the odd numbers that we're saying equal in shortcut n squared. So the base case, we have to consider the base case, and our base case in this case is the smallest value of n that we could possibly have. Well, we could have n equals 0, we can't have n equals -1. We can have n equals 1, but that's not the smallest possible case. N equals 0 is the smallest possible value that we could have here. So what we have to do here is we just have to show that basically if you sum from I equals 0 to 0 of 2i plus 1, that's going to equal, and I'm going to put a question mark above the equal sign right now because I am just trying to see whether or not this is true. So does the left side and the right side produce the same value? Well, we already know when I is 0, this is going to be 2 times 0 plus 1, and that's the only term in that sum because I'm stopping with I equals 0, and that comes out to 1 right there. So I'm testing whether, I'm sorry, not 0 squared. We said n plus 1 squared, not n squared. N plus 1 squared quantity like this. So this will be n plus 1, 0 plus 1 squared. And we know that 0 plus 1 squared is 1 squared, and 1 squared does indeed equal 1. Therefore, my formula works for the base case, n equals 0. Our inductive step This second step is called the inductive step. So suppose this statement is true for some arbitrary integer n. That is, what we mean by this statement is that assume that this sum works from I equals 0 to some arbitrary endpoint of the expression 2i plus 1. And so, in effect, what that would mean is that if this worked for that value of n, so I should say n equals k, which is an integer, then that would mean that that expression would be k plus 1 squared. So again, I'm just picking some arbitrary integer out there. I'm not specifying what it is. I don't want to specify what it is because of the fact that if I did specify what it is, then I'd only be establishing the truthfulness of this equation for that particular value. So here's where we get to have some fun. Now we need to prove this is true. The equation is true for n equals k plus 1. Well, the way I'm going to do that is I am going to say, use my assumed step. I know that this is now an assumed fact. Again, this is a trivial step. This didn't actually violate anything or prove anything. We've just said that suppose you can do it for some n equals k. Let's see if we can use that to prove for n equals k plus 1. So what would this look like? Well, our sum would go from I equals 0 to k plus 1 of 2i plus 1. And so what we would expect that to look like is, let me actually erase this and write this in a different color to put emphasis on this. We want to establish, is this relationship going to be true? That is, if I let n be k plus 1, that would just mean that I would have to replace n here with k plus 1. And so what I will have is parenthesis k plus 1 in for n plus 1 squared. So this is what it should equal if I increase this ending index by 1 unit, then that should just increase this value by 1 unit, and the formula should still work. But I don't know that these two things are equal to each other. I do see that this guy here is equal to k plus 2 squared, but I don't yet know whether these two things are equal to each other. So what I'm going to do is I'm going to try to use this inductive step here to help me, or this assumption step to help me. And the first thing that I'm going to observe is that a summation from I equals 0 to k plus 1 could actually be written like this. So this is equal to 1 plus 3 plus 5 plus etc. until you get to 2k plus 1, right? So that is when I plug in k for I, but that's not the last term, because the last term is where I is k plus 1. So what I actually have to also add to that is 2 times quantity k plus 1 plus 1. That's my last term in the sequence. So now not only are we going up to k, which would be the term 2k plus 1, but we're going up to k plus 1, which would be the term 2 times quantity k plus 1 plus 1. The reason we write it like this is because what I want to do is I want to show that this right here is really just the sum of the first k odd numbers. And that basically summing to the k plus 1th, or k plus 1st odd number, just means that I can sum the first k odd numbers and then add to that the k plus 1th. odd number. So all I've done really is just decompose that sum. And the reason I did this is because I want to try to rewrite this sum into what I have up here. We actually see that I have exactly from I equals 0 to k of 2i plus 1 equals k plus 1 squared. Well, hey, now that means I can substitute this out, and I can say, well, this right here equals k plus 1 squared. And now over here I have this extra term of 2 times k plus 1 plus 1. Now what I'm still trying to do is look at these two, this one here and this one here, and say, well, are they the same? Because I'm trying to show that the two sides end up equaling each other. And the trick here is really to break this summation up into non-summation pieces and typically make the summation look like what's on the right-hand side. So let's we can do a little bit more work on this k plus 2 squared. If we FOIL this out, we have k squared plus 2k plus 4. And if we work on this guy here, do we also get k squared plus 2k plus 4? Well, let's check it out. So I'm going to write some equal signs here to indicate that we're referencing this guy here. And so if I FOIL this out, I'll have k squared plus 2k plus 1. Here when I distribute, I'll have 2k plus 2 plus 1. And when I add those together, I have a 2k and a 2k there. So that's k squared plus 4k. And then I have oops, I made a mistake over here. This should be k squared plus 4k plus 4, because I'll have in k plus 2 times k plus 2, I'll have a 2k that happens here and a 2k that happens there. So here I'll have k squared plus 4k, and then I have plus a couple of singles, and then a plus 2 here. And when we add together those constants, we get plus 4. And check it out. We did it. We showed that the two sides are equal to each other. We broke down this summation into k squared plus 4k plus 4. The right-hand side, which we were checking to see if it would be equal to, is also k squared plus 4k plus 4. Therefore, here's what we can say. So this equation is true for n equals 0, the base case. With that, if we assume the equation works for some arbitrary n equals k, then the equation also works for n equals k plus 1. So that's what we've proven. We've proven these tidbits. So by mathematical induction, this equation works for all n greater than or equal to 0. And we're done. We've just established that our observation of how to sum together a bunch of odd numbers seems to be working for every single value of n, and so we can say that our claim is solid now. Let's take a look at one more in such investigation. Let's say that we want to sum together the even integers, So now instead of adding together integers of the form 2i plus 1, we just add together integers of the form 2i. So again, with respect to what this sum actually is saying, when you sum together from I equals 1 to n, for I equals 1, we're adding together 2 times 1. Then if I equals 2, that's going to be 2 times 2. I equals 3 will be 2 times 3, and so on. You can see that this is just 2, 4, 6, and onwards to I equals n, which will be 2 times n. So that'll just be the form of an even number. So if we do that for the first few to kind of look for a pattern, we see that when I is 1, this is just going to add together, well, it's not going to add anything, it's just going to be the first even integer. Here we'll have the first 2, which is 2 plus 4. This will be 2 plus 4 plus 6, which is 12. And this one will just add 8, which is 20. This one will add 10, which is 30. And this one will add 12, which is 42. And so it seems if we increase n by 1, we're basically adding some multiple of 4 to our values. So here, notice the pattern from n equals 1 to n equals 2 is that we added 4, and then 6, and then 8, and 10. So if we express that component that we're adding back to the n, we can see that the value that we're adding to get from n equals 1 to n equals 2 is actually related to this value of n here. If I double the value of n, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So it seems as though what I need to do is perhaps look for a connection between the n's. One maybe thing that isn't super obvious here is that if you look at where 2 comes from, and we stare at this table long enough, if I multiply 1 and 2 together, I get 2. If I multiply the next two indices together, I get 6. 3 times 4 gives me 12. 4 times 5 gives me 20. So it seems like that for the current value of n, if I multiply the current value of n by n plus 1, I'm going to get exactly that next value. So we're going to make the claim as follows. We're going to say that the sum of the integers, even integers, from I equals 1 to n is simply going to be n times n plus 1. And I can see that here, that in this case, 1 times 2 gives me 2. For n equals 2, I want a sum of 6, but if I take 2 times 3, I get 6, which is n times n plus 1. To get 12 for n equals 3, if I multiply that current value of n by an n larger by 1 unit, then I get 3 times 4, which is 12, and 4 times 5, which is 20. So once again, this in plain sight seems to work. 5 times 6 is 30, 6 times 7 is 42, but I cannot prove this is true for all n just based upon that, because at some point this logic might fail. And to avoid that, we want to prove this statement that this is going to equal n times n plus 1. So we're going to do it again with the mathematical induction, because we want to say that this is true for all n, and n greater than or equal to 1, because n equals 1 is the smallest index we can have. We can't go from I equals 1 back to 0. We can only go upwards in our index. So the base case that we need to prove here is for n equals 1. And this is always the fun one, the simple one to prove. From I equals 1 to 1 of 2i, does that end up equaling what we get if we take the n times n plus 1? So let's check. So from I equals 1 to 1, that's just the term 2, and 1 times 2 is 2, and 2 equals 2, therefore we have a go on the base case. If we were ever to fail the base case, then we know that our claim is not good. If this did not match up, then proving this theorem, or proving this equation is always true for all n greater than or equal to 1, would not be very valuable. We'd either need to pick a different base case or reevaluate our logic of whether or not this works. So again, we're going to do the inductive step. So assume the equation works for some arbitrary n equals k, where k is just some arbitrary integer. So what that means is the formula that we assume is true is that the sum from I equals 1 to k of 2i is going to equal k times k plus 1. So now we've fixated on a particular value of n. That value of n is k. And so you can see we're just replacing all the n's with k because that's where our sum stops. So we're assuming that this is true. And what that allows us to do when we prove for n equals k plus 1 is that I'm going to eventually use this as a mathematical substitution. In our checkerboard tiling problem, we did kind of the same thing, except it wasn't an algebraic substitution. It was a logical substitution where we created 4 of those n equals k cases in our n equals k plus 1 case. So we must show that this equation works for n equals k plus 1. Okay, so that is, I want to show that the sum from I equals 1 to k plus 1 of 2 times quantity k plus 1, I'm sorry, of 2 times I, k plus 1 is a constant, I is a variable, that I want to show, does that equal, well, okay, so here I'm going to replace, here I replaced n with k, so back here we need to replace n with k plus 1. So here we have k plus 1, and that means that in my product I'm going to have a k plus 1 times quantity k plus 1 plus 1. Okay, and the reason that is just going back to our formula up here. If the sum goes, whatever the sum goes up to, that's the value that gets plugged in over here. If our sum goes from 1 to smiley face, then this would be smiley face times smiley face plus 1. So all we're doing is replacing the maximum index n with the maximum index here and here. And we haven't shown this is true. We want to establish that this works. So once again, what we're going to do is we'll probably clean up this right side and distribute this out a little bit. And then we'll also break up this k plus 1 sum into a sum that goes up to k. So let's go ahead and do that first. So we know that this sum from to k plus 1 will be 2 plus 4 plus 6 plus ... Plus, once we get to the kth term, we'll have 2 times k. But we're not stopping at 2 times k. That would be this sum right here. We're stopping at k plus 1. So our next index value will be the next even integer when I is k plus 1. And so what we're going to do, like we did in the previous problem, we're going to take these terms here and we're going to say, well, hey, wait a minute, that's the sum from I equals 1 to k of 2i, and that this extra thing here is just plus some residual, that's plus the next even number beyond the kth term. And once again, right over here, we can kind of continue breaking this down, and we see that this is k plus 1 times k plus 2. If we FOIL that out, we'll have k squared plus 3k plus 2. And so guess what we're going to do here? Well, we don't have equality yet from the summation to the written out in non-summation form, so we've got to do some substitutions here. Well, hey, this thing here, the sum from I equals 1 to k of 2i, is by our assumption step equal to k times k plus 1. So what I can do is I can replace this with k times k plus 1 plus 2 times k plus 1, and I want to ask myself, does that equal k squared plus 3k plus 2? And let's do some math on this. Distribute, we'll get k squared plus k. Distribute, we'll get plus 2k plus 2. Combine like terms, we get k squared plus 3k's plus 2. And guess what? Those two sides are equal to each other. And we've just proven the inductive step that if it works for n equals k, the equation is going to work for n equals k plus 1. So our conclusion is the same. This equation is true for n equals 1, the base case. With that, if we assume the equation works for some arbitrary n equals k, then the equation also works for n equals k plus 1. By mathematical induction, this equation works for all n greater than or equal to, 1. And you see this inductive process is very much the same. The inductive step is the tricky part, but have faith in the process that this does, in fact, even though it's 3 steps, and it seems like for 3 steps, you shouldn't be able to get that much bang for your buck, but it really is true. Enjoy.